Alright, so this video is going to be covering Chapter 2, which deals with kinematics. More specifically, we're going to be looking at one-dimensional kinematics today. Now, in one dimension, you don't really have to worry about all the different components of 3D or 2D vectors. So, for the intents and purposes of this video, we're not going to worry about components, and we're simply going to use positive to indicate one direction, left or right, up or down, and negative to indicate the other direction. So these could also be, if you're falling, positive could be up or down, and then negative would be the reverse of that. Now, kinematics looks mostly at motion. So there's two very important components to motion, the first of which is velocity, and because we use SI units, we're going to be using velocity in terms of meters per second. How much distance you travel in how much time. Our next unit that we're mainly going to be dealing with is acceleration, which is change in velocity, represented by delta V, per unit time. So in this case, you have your velocity, which is in meters per second, over how much time it takes to change. So meters per second, or meters per second cubed is going to be our SI unit. And the first sort of concept we're going to be looking at very basically is average velocity. And so if you'll remember the average value theorem from calculus, it basically says that the average value of a function is basically its integral divided by how long that interval is. So you take the total area under a graph and divide that by how long that graph actually is. And so for velocity, to find the average velocity, all you have to do is substitute these x's for t's, because velocity is a function of, or the velocities we're going to be looking at are functions of time. So to find, your average velocity, all you have to do is take the integral from your 2 times of your velocity as a function of time equation and divide it by how long that interval is. Now, when you integrate velocity, you should know that the integral of velocity gives you a position equation, which you may have studied in Calc AB or BC or what have you. Similarly, integrating acceleration will give you a velocity, and differentiating will do the opposite. So differentiating will give you velocity from position and acceleration from velocity. But going back to our average velocity equation, we can note that we're integrating velocity from time 1 to time 2. So what you'll get is that you get x of basically your position at time 2 minus your position at time 1 over the total time 2 minus time 1. And we can write these, because it's a change from its final position, or from its initial position rather, to its final position, we can write this as a change in x, and this time as a change in time. So its an average velocity will be total change in x. In other words, if you start here and end here, you measure the displacement. So you don't measure how long you actually ran to get there. You could take, this weird route to get there. But the delta x, the displacement, will always be the distance, the net distance you traveled, which would be that straight line. So it's displacement over time is your average velocity. And now just for a quick illustration of the difference between velocity and speed, we'll use an example of a runner running around a track. So for example, if the runner starts here and does, 1, 2, 3, 4 laps and ends up back here, their total position, their displacement delta x, is 0, because they're at the exact same place they started. They could have gone absolutely nowhere and just stayed right here, or they can, take as many laps around as they want. So your total velocity, your delta x over delta t, will be 0 over your delta t, or 0 meters per second. In other words, you haven't traveled any total distance in a direction per unit time. However, with speed, we use the total distance, not the displacement. So, because speed is irrelevant of direction, basically you can treat these laps as though you've run 4 laps in a straight line. So in this case, your distance over time would be, 4 laps per however much time you took, or 4 laps per time, just as a general sort of statement. So just to clarify the difference between speed, velocity uses the total displacement, whereas speed uses the total distance. And one last note on average velocity, you'll often be given a position, x, versus time plot with some sort of path. In this case, you have this purple path curving gradually and this erratic sort of orange path. Now it should be noted, because both travel this total displacement, delta x, in this total time, delta t, they have the same average velocity, because their delta x over delta t equals basically the same thing, regardless of path you take. However, their instantaneous velocities, in other words, their velocities at different points, will vary greatly. So because we know that velocity equals delta x over delta t, if you measure, a sufficiently small time and likewise get a sufficiently small change in distance, like that, what you'll find is that velocity basically just becomes the derivative of position at any point. And if you'll remember from calculus, geometrically that translates to the slope at any given point is that velocity at, that t. So these can vary wildly in velocity at a given point. At this point, this one appears to be going somewhat backwards, but regardless of their varying instantaneous velocities, it's the total displacement over the total time that comes up with the average velocity. Moving on now, we're going to be looking at average acceleration, and this follows a very similar format to our formula for average velocity. So, as you learned probably in calculus, the integral of an acceleration gives its velocity. So in this case, you would have your final velocity minus your initial velocity over the total time it took for that velocity to change to get your basically the average value of your acceleration. And then from there, it's very similar. You get the total change in velocity over the total change in time, which gives you the average acceleration. Now, just to reiterate what we've sort of covered here, there exists a similar, or an analogous relationship rather, between position, velocity, and acceleration in terms of calculus relationships. So, going down the line this way, you derive position to get velocity as a function of time, and you derive again from that x position, which is now a velocity as a function of time, to get acceleration. Oppositely, you can integrate acceleration with respect to time to get a velocity, and then integrate that velocity equation with respect to time to get an initial x equation. Now, of course, you have to have these constants on the end that we'll discuss in more detail later on, because they take on a certain relevance. Alright, so moving on now to the sort of bread and butter of kinematics. We're going to be looking at equations for uniform acceleration. And what uniform acceleration means is that basically the acceleration is constant throughout the problem, or whatever time period we're going to be looking at. And then, just as a little side note, we're going to be using v0 to represent the initial velocity at time t equals 0, and x0 to represent the initial position at time t equals 0. Now we'll begin our derivation with a familiar equation, basically that acceleration is the derivative of velocity. Now we're going to do something what's known as the separation of variables. Basically, you take this tiny dt from under here, multiply both sides by dt, to bring it up over here by the acceleration. Those two cancel out, and you get a dt equals dv. Now what you can do is integrate to your initial conditions. So you start at time t equals 0 and go to time t equals t. So at any point in the future when t is some variable t. Likewise, you start with your initial velocity, which is v0, and go to whatever the final velocity is at that corresponding t, in this case v. And what you get is that at equals v minus v0. Now transforming this equation basically through addition, you get that v equals v0 plus a of t. And this, for constant acceleration, describes the velocity at any time given a initial velocity and the acceleration. From here, now, because we know that v equals the derivative of position, we can once again separate the variables. So we get that v dt equals dx, and then integrate once again. This time, because there's a dt over here, we integrate from time t equals 0 to any time in the future t. And because this is an x over here, we use, from its initial position x0 to any point x in the future. However, we have an equation for this v, so we can substitute that in and get the integral from 0 to t of v0 plus a of t equals, and then we'll just solve that one already, x minus x0. Now, integrating the left side of this equation, we get v0 times t. You just add on the t because of it's a constant in this case. But if you'll remember, you already have a t here, so you have to go up one exponent basically, and then add on a constant to cancel out when that exponent would come down in the derivative. So you get v0t plus a over 2 t squared equals x minus x0, or the position at any point in time given uniform acceleration is x equals x0 plus v0t plus a over 2 t squared. And both of these equations for x at any point in time and velocity at any point in time are key to describing a system with uniform acceleration. Now the last thing we're going to be discussing in this video is a time-independent equation. Basically because not all problems are going to give you how long it takes to change velocity or, change your position. So in this case, because we have two equations with the one unknown we're trying to get rid of, we can solve for t in terms of the first equation and then plug that t in to the second equation, in which case we get x equals x0 plus v0 v minus v0 over a plus a v minus v0 squared, a over 2, that is, over a squared. And what you can do is pause the video now and then solve this to derive a time-independent equation. Basically, you're solving for what will end up being a v squared term. So I'll let you pause it right now and solve that for yourself. Okay, so now that you've solved that, you can check against the final answer, which is actually v squared equals v0 squared plus 2a, and then this x minus x0 term you may have over here as something like that. We tend to abbreviate this whole thing just as delta x. So the final equation becomes v squared equals v0 squared plus 2a delta x. And these are the three main equations we use to describe uniform acceleration in kinematics.